And now I will pass over to Jonathan. So Jonathan Hirst is a professor in computational chemistry at the University of Nottingham. And Jonathan has been doing amazing work with the AI4Green Electron Lab Notebook, which PSDI have been involved with some of the case studies of. And today he's going to talk to you about how their ELN works. So over to you, Jonathan.
Great, thanks very much. And delighted to have the opportunity to share with everyone some of our work on AI4Green. It's an open source electronic lab notebook that we've developed over the last few years to promote sustainable chemistry. And I'm hoping that it's been already rolled out and deployed on the cloud, so you can access it via the link there. The source code's available, so if you prefer your own installation locally, maybe behind a firewall, you can do that. Has all the core functionality that one would expect to see in an electronic lab notebook. Yes, so in addition to that sort of core functionality, we've had a real focus on trying to promote awareness of green and sustainable considerations. So I'll show you some of that functionality. We've also responded to user feedback, so things like electronic signature for reaction approval sort of facilitates a move to paperless lab environment. So as you might imagine, the chemist sketches in the reaction they're thinking about doing. This will pop up a partially completed reaction table with as much data as possible pulled in from PubChem. We try to make data entry as painless as possible for the chemist. Boxes highlighted in red indicate where input is needed. Chemists like to think in equivalents, stoichiometric equivalents often, so that makes data entry easy if that's preferred. The hazard codes on the right-hand side there are pulled in from PubChem, and then the user needs to provide some data or information, including, for example, the physical form to inform the level of potential hazard. On the top half of this slide, you can see what you might expect in terms of a typical summary around the hazard. So there's a text summary of the hazards and then a matrix based on the level of hazard and the exposure potential to give an overall risk rating on the right-hand side. In addition to that, we also have then a summary table on sustainability considerations. So some of these can be calculated in advance of doing the chemistry, and then there's the opportunity for the chemist to maybe make some different decisions. And then once the chemistry's done, the chemist comes back to the ELN, updates information on yield, for example, and all the remaining metrics are computed and color-coded on the typical red, amber, green. If you don't like those colors, or for some accessibility reason, you can choose your own color scheme. And we see various components there around safety, temperature, whether the elements are rare or common, the types of chemistry, the isolation method, whether a catalyst is being used, and so forth. So these metrics are calculated automatically and have come out of a consortium from a few years ago called Chem21 that sort of provided a consensus assignment to different solvents, for example. So we have kind of two functionalities around solvents, and in R&D and pharma, for example, more than 50% of the cost of cleanup and waste disposal is associated with solvent. So this is a big consideration. On the top half, I'm showing our solvent guide. So this is sort of informative. If you choose a solvent from the drop-down menu, when you're defining your reaction, it will be color-coded. And if it's not green, that might prompt almost immediately the thought of, is there an alternative? You can click on the solvent flashcard, and this will pop up the summary that's shown in the red box there for an N-dimethyl acetamide. And there would be a list of possible alternatives, and you could pick one of those and look at the flashcard for the alternative side by side with your initial choice and decide if the various considerations were covered off by a greener alternative also. So these are the color coding there on the radar plot is around safety, health, and environment. On the bottom half, we have something that's a bit more cutting edge and interactive in terms of an AI or machine learning type tool. So maybe you've done more extensive exploration of your reaction performance in a set of solvents, and you want to understand those data a little bit more. Principal component analysis is a well-established approach for looking at these sorts of data and can be done on a sort of reaction class dependent basis. So you have a set of physiochemical properties that are relevant for your solvent and the reaction class. You plot those in 2 dimensions for visualization, and maybe you've made some empirical observations on yield, and you've got a solvent that's not so green and you want a greener alternative that would be predicted to be high yielding. Of course, AI and PCA aren't magic oracles of truth necessarily, so it might be your visualization in 2 dimensions doesn't reflect actually what you know about some of the similarities between solvents. And the interactive kernel PCA that we've implemented allows you to drag points around interactively on the principal component plot, and the machinery underneath will update the embedding, the clustering, the PCA plot that you're looking at in a mathematically rigorous way, imposing the constraints that the points you want close to each other are close to each other. So this can be quite a powerful approach, and we've given a few case studies in the paper that we published last year shown there. So the solvent selection is one area where there's some interesting machine learning tools supporting chemists making more sustainable decisions. Another functionality that we've integrated is based on AstraZeneca's open source AI Synth Finder. We've implemented some algorithmic improvements, and we've also layered on top again the sustainability considerations. So maybe you find several possible routes suggested by the retrosynthetic planning. You can look at each of those in turn and the color coding on the sustainability, and you can even break down individual steps within those routes on different considerations, for example, around solvent temperature, catalyst use, atom economy, safety, and you can upweight or downweight those as you prefer. So another, I think, powerful AI tool which chemists can interact with in an intuitive fashion without needing to know any of the underlying algorithmic detail. So we have a number of users across the UK and further afield. A lot of interaction with them as we continue to develop the code. And to maybe pick up on some of the aspects that have already been touched on in other presentations in the session earlier. How do we get that engagement with the desired user base, getting people to change from a way of working that they're already quite happy with, thank you very much, to some new way. That dimension of technology adoption is very challenging. So the idea is let's introduce this at an undergraduate level, and we've written a pedagogical version of the ELN where some of the functionality is repurposed and reused behind the scenes, but students need to work out more of the green metrics for themselves first and then be told or advised they've not got the calculation quite right, try again, identify the hazards again, advised if they've not got that right and asked to try again, and then the instructor can provide the feedback just at the final stage for that human expert in the loop oversight. So yeah, particularly tailored for use in undergraduate labs with a variety of functionality there. And again, a website where you could have a look at that if that were to be of interest. And we're working on making the code easier to use. So for a new instructor coming in with a new experiment, that they would be able to pick and choose what sorts of things they'd like the students to see in the app. So the QR code there takes you to the AI4Green app website. You can have a look at things there, and obviously happy to pick up any discussion points in due course. Thanks.
Awesome. Thank you very much, Jonathan.